In this video, we're going to review some of the topics that are typically covered in the first exam of organic chemistry. So let's go ahead and begin. This is methane, C2H6. If you see that, that's ethane. Sometimes it'll be written this way. You can also show with a line structure. C3H8, this is propane, which you can write the condensed structure like this. And if you want to write the bond line structure, it looks like this. Every endpoint in the bond line structure represents a carbon. C4H10, that's butane. C5H12 is pentane. C6H14, that's hexane. C7H16 is heptane. C8H18 is octane. C9H20 is nonane. And C10H22, that's decane. So you want to be familiar with the alkanes, the name of the alkanes up to decane. Now let's talk about IUPAC nomenclature. Let's say if we want to name this compound, what would it be? And let's do a few examples. Go ahead and name these molecules. So on the left, we have a total of, well, the longest chain has 6 carbons, so we want to name that first. That's hexane. And we have a methyl group on carbon 3. So this is 3-methyl-hexane. When numbering the parent chain, you want to number in such a way that it gives you the lowest number for the substituents. If we were to count it this way, it would be 4-methyl-hexane instead of 3-methyl-hexane. But we want methyl to have the lowest number. So 3-methyl-hexane is the answer. For the next one, if we were to count it this way, we would have a methyl on carbon 4 and 5. But if we count it the other way, we'll have methyls on 3 and 4 instead of 4 and 5, so we want to count it from left to right. Now, because we have a 7-carbon chain, this is going to be heptane. We got a methyl on 3, a methyl on 4, so this is going to be called 3,4 dimethyl heptane. So whenever you have a 1-carbon substituent, it's called methyl. When you have a 2-carbon substituent, ethyl, 3-carbon substituent, propyl, this is isopropyl. This as a substituent is sec-butyl, and this here is tert-butyl. So those are some other substituent names that you want to be familiar with. Now let's go ahead and name this one. Should we count it from left to right or right to left? What would you say? If we count it from left to right, this is going to be 4, 5. If we count it from right to left, this will also be 4, 5. So it doesn't really, if we count it in either way, we'll still get the same numbers for the substituents. But there's a difference here. We have an ethyl and we have a methyl. So for those two substituents, we want to put it in alphabetical order. E comes before M. And we want to put the 4 on ethyl and the 5 on methyl instead of the other way around. So in that case, it's better to number it this way. Because if you can have the substituents in ascendant order, that's going to be better. So the answer is 4-ethyl 5-methyl octane. If we were to number it the other way, ethyl would be on carbon 5, methyl will be on carbon 4. So when naming alkanes like this, you want to make sure that you put the substituents in alphabetical order. And if you get a situation like this, you want the numbers to be in ascending order. So 4-ethyl 5-methyl octane is better than 5-ethyl 4-methyl octane. Now for the next example, we have a total of 7 carbons. Now if we number it from left to right, the substituents will be 3, 4, 5. And the same is true if we number it from right to left. But Br alphabetically should be listed first, so we want that to be number 3 instead of number 5. So I'm going to number it left to right. So this is going to be 3-bromo, 4-chloro, 5-methyl heptane. So that's how we can name that particular compound. Go ahead and name that one. And while you're doing that, also work on this example too. So looking at the example on the top left, what you need to know is that we need to identify the longest chain. The longest chain is not 8 carbon atoms. Instead, the longest chain is here. So we have substituents on carbons 3, 5, and 6. If we were to number it the other way, the substituents will be 4, 4, 5, 7. Now looking at the first substituent, 3 beats 4. Now this 5 is higher than a 4, this 6 is higher than a 5, but this 6 beats the 7. So overall, we want the first number to be the lowest number. So this is going to be better, 3, 5, 6, 6 instead of 4, 4, 5, 7. So we have a methyl on 3, another methyl on 5, and 2 methyls on 6. So this is going to be 3, 5, 6, 6, tetramethyl. Di means 2, tri means 3, tetra means 4. So this is going to be tetramethyl nonane. Now for the next example, we need to identify the longest chain. And it's going to be 1, 2, 3, 4. It's not going to be this 1, 2. Well, actually, it could be that. So what do you do in a situation like this, where you have 2 chains that are equal in length? Let me number it in different colors, and then we'll talk about it. So if you have 2 chains that are equal in length, what do you do here? Well, let's look at the blue chain. You want to choose the parent chain with the greatest number of substituents. Here, this will be 1, 2, 3 substituents. Now, if we look at the red chain, we have 1, 2, 3 substituents. It looks like these might be the same. Here we have an ethyl group, a methyl group, and a sec-butyl group. If we look at the blue chain, we still have a methyl, ethyl, and a sec-butyl group. So it seems pretty identical, but let's go deeper. Let's look at the numbering of the groups. So for the red one, we have a methyl on 3, we have an ethyl on 5, and we have a sec-butyl, if you want to use the common name, on 4. To name it using IUPAC nomenclature, we're going to have to do something different, and we'll talk about that. Now, looking at the blue chain, we still have a methyl on 3, the ethyl is still on 5, and we have a sec-butyl on 4. So it really doesn't matter how we name it. So in that case, what I'm going to do is I'm going to focus on the blue chain because it's easier to look at it when it's going straight. But I'm going to redraw it. So we have a methyl on 3, sec-butyl on 4, ethyl on 5. Is it better to count it left to right or right to left? Ethyl comes before methyl, so we want the 3 on the E and the 5 on the M instead of the other way around. So I'm going to count it from right to left. Actually, no, this will give us 4, 6, so that's not going to work. It has to be left to right. It's better to have 3, 4, 5 instead of 4, 5, 6. So now let's name it. We have an ethyl on 5. We have a methyl on 3. Now instead of saying 4 sec-butyl, what we can do with this group is we can name this complex substituent. So starting from the parent chain, this is carbon 1, carbon 2, carbon 3. So that's a 3 carbon subchain, that's a propyl. And on carbon 1 we have a methyl. So it's a 1-methyl propyl group. Putting it all together, we have 5 ethyl, 3 methyl, and on carbon 4, so this is dash 4, and then in parentheses, a 1-methyl propyl group, and then the parent chain is octane. So now you know how to name alkanes. Now, for those of you who want to watch the full extended version of this video, which is about 2 hours long, feel free to check the description section for more info. There you'll get the links where you can access the full video on my YouTube membership program or on my Patreon membership program, whichever you prefer. So feel free to take a look at that when you get a chance. So here we have the condensed structure of a molecule. What is the functional group of this molecule? How would you draw it out? And also, what is the name of it? To draw it out, we have a carbon. Carbon likes to form 4 bonds. So this is a CH3 next to another carbon. Now we have a hydrogen and an oxygen. If you were to see CH3, CH2OH, this is an alcohol. If you were to see CHO, this is an aldehyde functional group. The way you would draw an alcohol is different than an aldehyde. So let's draw that alcohol. This 2-carbon alcohol is ethanol. Oxygen likes to form 2 bonds. Carbon likes to form 4 bonds. When oxygen forms 2 bonds, it likes to have 2 lone pairs, so a total of 8 electrons. Nitrogen likes to form 3 bonds and 1 lone pair when it's neutral. When they have charges, it's going to differ. Now, for this carbon to have 4 bonds, what we need is, this is not going to work if we wrote it like this. In order to have 4 bonds on the carbon and 2 bonds on the oxygen, we need a double bond O. And then it's going to work. So this is called ethanol with an OL. It's an alcohol. This is called ethanol with an AL because it's an aldehyde. What about this one? CH3COCH3. How would you draw that? So we have carbon on the left with 3 bonds to hydrogen. There's another carbon. And anytime you see CH3, it's always going to look like this at the end. So we don't want to draw it this way because carbon is going to have 2 bonds and not 4. So this is going to be another carbonyl group where we have a C double bond O. So drawing it this way, every carbon atom has 4 bonds. Oxygen has 2 bonds with 2 lone pairs, and the octet requirements are satisfied. So this is what is known as a ketone. And to name it, we have a 3-carbon ketone. So this is pentanone. The suffix ONE, ketone. Go ahead and try these 2 examples. Convert the condensed structure into a Lewis structure, identify the functional group, and name it if you want to. So here we have a CH3, which is going to be the same, and it's next to a CH2, a carbon with 2 hydrogens. And then we have a COOH group. When you see this, this is known as a carboxylic acid. It's going to have a carbonyl and a hydroxyl group combined. So drawing it this way, every oxygen has 2 bonds and 2 lone pairs. Carbon has 4 bonds, and hydrogen can only form 1 bond. When you see this CO2 next to another carbon, that is an ester. Whereas if you see CO2H, that's a carboxylic acid. So we have a CH3, then we have a carbon. The ester is going to look very similar to a carboxylic acid, but instead of the hydrogen, we have the CH3 group. So that's how we can draw that particular Lewis structure. Now to name it, this part here is known as ethanoate. 2 carbons, think of ethane. Here we have 1 carbon, think of methyl. So combined, it's called methyl ethanoate. So that's how you would name an ester. Now let's move on from drawing Lewis structures, but let's continue with identifying functional groups. Determine the type of alcohol that we have here. What is the difference between these 3 types of alcohols? Whenever you see an SH group, this is known as a thiol. This here is a primary alcohol because the carbon that has the OH is a primary carbon. That carbon is attached to only 1 other carbon. This is a secondary alcohol because the carbon that has the OH is attached to 2 other carbons. And this is a tertiary alcohol because the carbon that's the OH is on is attached to 3 other carbons. Now the situation with amines is different. So whenever you see an NH2 group, you're dealing with an amine. So this is a primary amine. This here, it's not a tertiary amine, it's a primary amine. When dealing with amines, you don't look at how many carbon atoms are attached to the carbon that bears the amine functional group, but rather you look at how many carbon atoms are attached to the nitrogen. Only one carbon is attached to the nitrogen here, and the same is true for this one. Only one carbon is attached to the N, and that makes both of them primary amines. Here's an example of a secondary amine. The nitrogen is attached to 2 carbon atoms, so that's a secondary amine. And the name for that is, here we have an ethyl group and here's a propyl group, so it's ethylpropylamine. This is an example of a tertiary amine. There's 3 ethyl groups on it, so it's tertiary because there's 3 carbons attached to the nitrogen. But this is going to be called triethylamine. So we talk about amines. Now, if we add a carbonyl functional group to it, this becomes an amide. If you have a halogen attached to an alkane, this becomes an alkyl halide. If you were to see this, C2H4, this is ethene. Whenever you introduce double bonds between carbon atoms, you get what is called an alkene. C2H2, this is acetylene, and we have a triple bond between the 2 carbon atoms. This is an alkyne functional group. So now you know the common functional groups: amines, amides, carboxylic acids, esters, ketones, aldehydes, alkyl halides, alkanes, alkenes, alkynes. This will be an alkane if there's no special functional group. And the next thing you need to be familiar with is an aromatic ring. Now, for those of you who want more examples on functional groups, there's a video that I have on YouTube. And if you go to the YouTube search bar, if you type in unusual functional groups, organic chemistry tutor, it should come up. So that has a bigger list on this topic for those of you who are interested in that. So feel free to take a look at that when you get a chance. Some other examples include anhydrides. And there's some other ones, but I'll stop it there. I was going to say anhydrides and ethers, but you'll find that in the other video for those of you who are interested. This one is called ethyl propyl ether. Now let's move on to hybridization, as well as bond angles and geometry. What is the hybridization at each carbon atom? Also, determine the bond angles and molecular geometry. So to find the hybridization at this carbon atom, we need to count the number of groups it's attached to, also known as the steric number. So it's 1, 2. We would count this whole thing as one group, even though there's a triple bond here. So that carbon has a steric number of 2. It's attached to 2 groups. So it's going to be sp hybridized. If the steric number is 2, it's s1p1. 1 plus 1 adds up to 2. If the steric number is 1, typically that's just s. If it's 3, it's going to be sp2, 4, sp3. 1 plus 3 adds to 4. 5, you're probably not going to see this in organic chemistry, but in general chemistry, you'll see it. D1sp3. 6, D2sp3. 2 plus 1 plus 3 adds up to 6. This carbon has a steric number of 2, so it's going to be sp hybridized. This one has a steric number 3, 1, 2, 3, so it's going to be sp2 hybridized. This has a steric number 4, 1, 2, 3, 4, so it's going to be sp3 hybridized. This hydrogen is simply S, and the oxygen has 1, 2, 3, so a steric number of 3, it's sp2 hybridized. So that's a quick and simple way to determine the hybridization on an atom. Now, on a test, if you're asked to find the orbital overlap of a bond, so let's say for the CH bond, let's put the answer here. This hydrogen has an S orbital. It's not really a hybrid orbital because it's just pure S. This carbon has an sp hybrid orbital. The reason why we call it a hybrid orbital is because it's a mixture of an S and a p orbital. So that's a hybrid orbital. So to form this bond, we're going to overlap an S orbital with a hybrid sp orbital. So the orbital overlap of the bond is S, sp. If we want to find the orbital overlap of this bond, we simply look at the two atoms that connects that bond together. So that bond represents the overlap of an sp2 hybrid orbital with an sp3 hybrid orbital, as we could see here. So that's how you could determine the orbital overlap of a bond. Now let's talk about bond angles. For an sp hybrid carbon, the bond angle is going to be 180. The molecular geometry is linear. For an sp2 hybrid carbon, the bond angle is going to be around 120. That's an approximation because it can vary slightly based on what it's attached to, but the approximation is 120. The molecular geometry is trigonoplanar or trigonoplanar. Now for an sp3 hybrid carbon, this is going to be very close to methane. The bond angle for methane is 109.5. The molecular geometry is tetrahedral. So typically you're going to be tested on those type of bond angles and those molecular geometry names. Now let's go back to the structure because there's another question that we can ask related to it, and that has to do with the length of a bond and the strength of a bond. So what you need to know is that triple bonds are stronger than double bonds. 2 bonds is stronger than 3. Let me say that again. 3 bonds is stronger than 2. So triple bonds are stronger than double bonds. Double bonds are stronger than single bonds. 2 bonds are stronger than 1. So bond strength increases to the left. Bond length increases to the right. What that means is that triple bonds, they're the strongest, but they're the shortest. Single bonds are the weakest, but they're the longest. A triple bond has 1 sigma bond and 2 pi bonds. A double bond has 1 sigma, 1 pi, and a single bond only has a sigma bond. With that information, how many sigma and pi bonds are in the structure? To count the sigma bonds, this is going to be 1, 2, 3, 4, 5, 6, 7, 8. Every bond has 1 sigma bond. So we got 8 sigma bonds. How many pi bonds are in this structure? What would you say? The double bond has 1 pi bond, the triple bond has 2, so we have a total of 3 pi bonds. Now, out of all of these bonds, which one would you say is the shortest? The triple bond is going to be the shortest bond, but it's also going to be the strongest. Now, which of these, now let's look at these 2 single bonds. which one is longer and which one is stronger? The one on the left or the one on the right? This is when we have to use hybridization to figure out the answer. This is an sp hybrid carbon, this is sp2, and this is sp3. The bonds associated with an sp carbon, those are typically triple bonds. They tend to be shorter and stronger. The bonds that are associated with an sp3 carbon tends to be single bonds, so they tend to be longer and weaker. So when we compare two single bonds, one which is an overlap of an sp and an sp2 hybrid carbon, the other one is an overlap of an sp2 and an sp3 hybrid carbon. The sp2 are the same, so we're looking at the sp carbon, which is typically associated with a shorter, stronger bond, and an sp3 carbon, which is typically associated with a longer, weaker bond. We could say this bond here on the left, because part of it is from an sp carbon, this bond is going to be stronger and it's going to be shorter. The other one, which is associated with an sp3 carbon, that one is going to be weaker, but it's going to be longer. So remember, as the strength of the bond increases, the length of the bond will decrease. They're inversely related. Now let's talk about formal charge. Let's calculate the formal charge of every colored atom. So this is a thiolate ion. Let's calculate the formal charge for that. Let's use a different color here. This is an amine, but it changes when we add a hydrogen. So let's calculate the formal charge on the nitrogen. The formula for formal charge, it's equal to the valence electrons minus the bonds plus the dots. So focusing on the sulfur, sulfur is in group 6A of the periodic table. It's the same group as oxygen, it's a chalcogen. Group 6A or group 16, those elements typically have 6 valence electrons. In this structure, we see that sulfur has one bond, and there's 3 lone pairs, which equates to 6 dots. So this is going to be 6 minus 7, which is -1, and for some reason I've already, through habit, put the negative charge there. But that's how you would calculate the formal charge using this formula. Now let's do the same thing with the nitrogen atom. Nitrogen is found in group 5A or group 15 of the periodic table, so it has 5 valence electrons. In this structure, it has 1, 2, 4 bonds. It doesn't have any dots, so no lone pairs. Thus, it's going to be 5 minus 4. We get +1. So it has a positive formal charge. This right here is known as a sulfonic acid. I'm going to draw sulfonate without the hydrogen, but one particular resonance form of the sulfonate ion. What is the formal charge on the sulfur for this particular resonance form? So using a formula, we know that sulfur has 6 valence electrons. In this structure, it has 4 bonds. It doesn't have any dots on it. So it's going to be 6 minus 4. It's going to be +2. Or 2 plus. So that's the formal charge on the sulfur atom. Now let's move on to the next topic. Resonance structures. What you need to be able to do is you need to be able to draw resonance structures. You also need to know how to identify the major resonance contributor, as well as draw the resonance hybrid. So let's do that with this example. Let's begin by drawing the resonance structure, and we would use a double arrow to indicate that. Now, when drawing a resonance structure, you can move electrons, but you can't move atoms. So we're going to take these pi electrons in a pi bond and move it towards a plus charge. The arrow represents electron flow. A full arrow represents the flow of 2 electrons. A half arrow represents the flow of 1 electron. Electrons typically flow from a region of high electron density to a region of low electron density. So in this structure, it's going to flow from a nucleophilic region to an electrophilic region. Electrophiles tend to be positively charged or electron deficient. Nucleophiles tend to be negatively charged or electron rich. A double bond is more nucleophilic than a positive charge. Neutral is more nucleophilic than a positive charge. As we move the double bond here, this carbon lost the bond, so it's going to be electron deficient. It's now going to have the positive charge. So what we have here is the secondary allylic carbocation, and here is the tertiary allylic carbocation. Tertiary carbocations are more stable than secondary carbocations due to hyperconjugation being one of them, and also the inductive effect. So those are the only 2 resonance structures that we can draw. Now, which one is the major resonance contributor? The major resonance contributor is going to be the one that's more stable. Since tertiary carbocations are more stable than secondary carbocations, this resonance structure will be the major resonance contributor. The other one will be the minor resonance contributor. Now, to draw the resonance hybrid, here's what we're going to do. We're going to draw the atoms that did not move. Now, notice that the pi bond is between these 3 carbons. It can move anywhere among those 3 carbons. So we're going to use a dash bond to indicate that. So in actuality, the pi bond is shared among those 3 carbon atoms. Now the plus charge is shared between this carbon, the tertiary carbon, and the secondary carbon. So this would represent the resonance hybrid of these 2 resonance structures. Now let's try another example. Go ahead and draw the resonance structure for this ion and identify which one is the major resonance contributor and draw the resonance hybrid. This carbon has a partially positive charge. The oxygen has a partial negative charge. Oxygen is more electronegative than carbon. So this negative charge, the electrons there are going to be attracted to the partially positive carbon atom. So this is like the nucleophilic center, and this is an electrophilic region. So the electrons are going to flow towards the electrophilic region of that molecule. So this lone pair is going to flow towards the carbonyl functional group. This pi bond is going to break. Those electrons are going to be pulled towards the more electronegative oxygen atom. So we're going to get this particular resonance structure. And here is the pi bond. And now the oxygen bears the negative formal charge. So that's the resonance structure that we can draw. This is known as the enolate ion. Now, which one is the major resonance contributor? Is it the one on the left or the one on the right? Which one is more stable? Is it better to put a negative charge on a carbon atom or on an oxygen atom? What would you say? So here's carbon and here is oxygen on a periodic table. They both exist in the second row. And electronegativity increases to the right towards fluorine. Oxygen is more electronegative than carbon. Here are the EN values for that. So because oxygen is more electronegative, it can better handle that negative charge. So putting the negative charge on the oxygen creates a more stable situation than leaving it on a carbon atom. So this is less stable, and this particular resonance structure is more stable, which makes it the major resonance contributor. So the resonance hybrid is going to look more like this than like that. So the true structure, which is somewhere between those two molecules, is going to look more like this one because that's the more stable resonance structure. But let's draw the resonance hybrid. This oxygen will always have at least 2 lone pairs. And this structure has 2 lone pairs, and this one it has 3, but it will at least have 2. The pi bond will sometimes be here and will sometimes be here. So the pi bond can move between the oxygen and these 2 carbon atoms. So we're going to draw a dashed line among those 3 atoms. That shows that the pi bond is shared among those 3 atoms. Now the negative charge is shared between the carbon atom and the oxygen atom. So both of those atoms will have a partial negative charge. And that right there is the resonance hybrid.